We presented the P0 epsilon problem and met several approximation algorithms that aim to solve it. We now turn to theoretically analyze this problem and these algorithms. Our broad goal is to generalize theoretical claims we have posed for the P0 problem, and the starting point is the issue of uniqueness. Our path took us from the P0 problem to its approximate version, P0 epsilon. We justified this migration in several ways, and we feel much more comfortable now in defining our prime goal as handling P0 epsilon. The question we pose now refers to the issue of uniqueness of the solution of this problem. Recall our statement about P0 having a unique solution. It started with a given linear system characterized by A and B. The vector B is created as A times x naught, where x naught is sparse. Now, given A and B, we seek the sparsest solution to the system Ax equals B. Our analysis led us to the conclusion that if x naught is sparse enough, then it is necessarily also the sparsest possible. The bound on the cardinality of x naught was posed in terms of the mutual coherence of A. Our goal now is to derive a similar statement for P0 epsilon. Can this be done? As we are about to show, the answer is negative. However, another closely related property of stability can be posed. Let's construct a simple example that will illustrate the difficulties with P0 epsilon. A is this matrix of 2 rows and 4 columns, and x naught is a vector of length 4 with only one non-zero. The vector B is given as A times x naught, and since we are dealing now with the approximate problem, we can assume that B is slightly perturbed by an additive noise of limited energy. Given A and B, our goal is to solve P0 epsilon, that is, finding the sparsest solution x that will bring Ax to be epsilon away from the vector B. In our case, epsilon is the noise norm, 0.5. The dream is to get that x0 emerges with all its glory as the solution of this problem. We will use a geometrical illustration to show how the solution of P0 epsilon is obtained. All our discussion will be now presented in 2D, the domain of the vector B. First, we draw the 4 columns of A. These are our atoms. The lines passing through the origin and aligned with these atoms represent possible vectors A times x, where x has cardinality 1. Recall that our x naught has a value 2 in the third entry, and thus Ax naught is clearly positioned on one of those lines, as described. We added noise of norm 0.5 to Ax naught in order to get the vector B, and thus this disk represents the possible positions of the vector B. Let's assume that this is the location of the actual B we got. We are given A, B, and epsilon, and we aim to solve the problem P0 epsilon. The constraint in this problem puts yet another disk of the same radius around B, defining possible locations of the vector A times x. However, we are searching very sparse x vectors. Considering locations referring to cardinality 1, these are highlighted in the 2D plane. Thus, the intersection of the red disk and these lines forms the set of possible solutions. This intersection is marked clearly in green, and every point in it represents a candidate solution, all having a single non-zero in x. Several things can be observed here. First, there is no unique solution, but rather a set of them. Secondly, the original x naught is included in this set, but it is only one among many possibilities. Thus, rather than aiming to claim that the solution of P0 epsilon is unique, which is clearly not, let's change our goal. Let's claim that the obtained solution is not far from the original x naught. We will refer to this as the stability property. We return to the example we have just presented and change one thing. The energy of the noise is now bigger. This implies a wider disk. As before, B is given as a point somewhere in this disk. Turning to solve P0 epsilon, we draw the locations of Ax around B as before and get this red disk. The situation now is substantially different, since the set of candidate solutions is wider and could rely on 3 different atoms. This means that we start with a vector x0 that has a specific support and end up solving p0 epsilon and getting a different support. This exposes the sensitivity of our problem to the noise level. By the way, if the noise would have been stronger yet, the red disk would have overlapped the origin. What happens in this case? Then the zero solution is the optimal one, having cardinality 0.